We physicists have held up 100 years, beginning around 1916, for this photograph. A neighborhood dim opening might just be perhaps one of the most spellbinding and confounding characteristics known to man. They are colossal beasts concerning gravity and, simultaneously, all things considered, vague to us. A dim opening weighing perhaps 2 to multiple times the mass of the Sun. However, considering the exploration that was placed into them over the last several decades, we've gone from knowing almost nothing about them to progressively understanding more. Recently, things have gotten more fascinating. Miss Kaku revealed that we finally got a look at what's inside a dim opening. This new information sheds light on the nuances the universe of science might have missed initially. Join us as we dive further into dim openings and uncover what's inside. What are dim openings? Before we dive into the subtleties of what Michio Kaku found, we need to examine the basics. Although most of us have some idea of what dim openings are, there are still a few gaps in our understanding. In 1916, Albert Einstein published his theory of general relativity, which predicted the existence of dim openings. At that time, the idea of dim openings was completely speculative. It took 50 additional years for the scientific community to find evidence that dim openings truly exist. This happened during the 1960s, when they were studying the Cygnus X-1 celestial body and observed an oddly bright blue star emitting X-rays. This star was not a flat object, but was orbiting a massive, dim something. Upon further investigation, it was found that the X-rays weren't moving around on their own. They were being sucked into the dim object they were orbiting. Hence the name dim opening. This discovery was groundbreaking because it provided evidence that dim openings truly exist and weren't a figment of Albert Einstein's imagination. While that was incredible, it also meant that there was this mysterious entity in space that scientists urgently needed to understand. Cygnus X-1, located in the constellation Cygnus, about 6,000 light-years from Earth, was no small discovery. It is many times brighter than the Sun and incredibly dense, giving it a powerful gravitational pull. This gravitational force is so strong that not even light can escape it. Hence the term dim opening. The mystery deepens. The concept of a dim opening is both fascinating and terrifying. It is a region of space where gravity is so strong that nothing, not even light, can escape. Whatever gets too close to a dim opening is pulled in, disappearing forever. This danger makes it all the more critical to learn everything we can about them. After discovering Cygnus X-1, researchers began looking for other dim openings. They found that there might be nearly 100 million dim openings in the Milky Way alone. However, because they are so incredibly difficult to detect, we still don't have an exact number. It appears that there are several million dim openings in our own galaxy, making them all the more important to study. Layers of a dim opening. In 2019, scientists managed to capture the first clear photograph of a dim opening, the M87 dim opening. This image, compiled over several nights, revealed that dim openings have 3 layers, contradicting the popular belief that they are simply vast voids of nothingness. 1. The event horizon. This is the point of no return. Once an object crosses the event horizon, it is inevitably pulled into the dim opening. 2. The photon sphere. In this region, light circles the dim opening due to its intense gravitational force. 3. The singularity. At the core of the dim opening, everything that enters is compressed to an infinitely small point. The singularity is where the laws of physics, as we know them, break down, and we cannot predict what happens next. Challenges in studying dim openings. Studying dim openings is extraordinarily challenging. Traditional scientific methods do not apply due to their unique nature. Sending probes into a dim opening is impossible because anything that enters the event horizon is pulled toward the singularity and compressed into nothing. Instead, researchers must rely on indirect observations, such as studying the radiation emitted and the gas and dust surrounding these objects. Despite these challenges, scientists continue to develop theories and gather data about dim openings. Theories about formation. One compelling theory is that dim openings are formed from collapsed stars. When a star exhausts its fuel, it can no longer generate enough energy to counteract the force of gravity pulling inward. The star collapses, becoming denser until it forms a singularity. In 1963, New Zealand mathematician Roy Kerr proposed solutions for rotating dim openings, further advancing our understanding. Dim openings remain one of the most fascinating mysteries of the universe, offering endless opportunities for discovery and exploration. The work of Roy Kerr, along with other pioneering scientists, laid the groundwork for understanding rotating dim openings, or what are now known as Kerr black holes. These are black holes with angular momentum, meaning they rotate rapidly around their axis. This rotation introduces additional complexity to the already mind-bending nature of black holes, as it distorts the surrounding space-time even further. Kerr black holes exhibit unique features, such as an ergosphere, a region outside the event horizon where space-time itself is dragged around the black hole. This phenomenon, called frame dragging, allows particles to gain energy and escape the black hole's vicinity, making Kerr black holes some of the most fascinating objects to study. How do we study dim openings today? Despite the challenges, technological advancements have allowed us to gather more detailed data about black holes. One of the most groundbreaking achievements in recent years was the creation of the Event Horizon Telescope, EHT. This global network of radio telescopes effectively acts as a single, planet-sized observatory, capable of capturing high-resolution images of black holes. The first image of the supermassive black hole at the center of the M87 galaxy was released in April 2019. This historic photograph showed a glowing ring of gas and dust surrounding a dark shadow, the black hole's event horizon. This achievement was monumental, as it provided direct visual evidence of black holes for the first time. What lies beyond the event horizon? While we now have images and a better understanding of black holes, the question of what lies beyond the event horizon remains unanswered. The singularity at the center is a point of infinite density where the known laws of physics break down. Some theories suggest that singularities could be gateways to other universes or even to different points in space-time. This idea is often explored in science fiction, but remains purely speculative due to the lack of direct observational evidence. Other researchers propose that the singularity might not be an infinitely dense point, but rather a region governed by unknown quantum gravitational effects. These effects, which require a unified theory of quantum mechanics and general relativity, could potentially explain the true nature of black holes and their inner workings. Black holes as cosmic engines. Interestingly, black holes may not just be destructive forces. They could also play a vital role in the universe. Supermassive black holes, like the one at the center of our Milky Way galaxy, are thought to influence the formation and evolution of galaxies. These black holes generate immense amounts of energy by accreting matter, producing jets of particles and radiation that extend across vast distances. These jets can regulate star formation and distribute elements throughout the cosmos, shaping the large-scale structure of the universe. The future of black hole research. As technology continues to improve, so does our ability to study black holes. The James Webb Space Telescope, JWST, has already begun contributing to this field by observing the environments around black holes with unprecedented detail. Additionally, next-generation gravitational wave detectors like LISA, Laser Interferometer Space Antenna, are expected to provide deeper insights into the collisions and mergers of black holes. Furthermore, advancements in quantum computing and theoretical physics could eventually help us unlock the mysteries of the singularity and develop a unified theory that explains the behavior of black holes. Black holes are no longer just theoretical constructs. They are real, observable phenomena that challenge our understanding of the universe. With every discovery, we come closer to unraveling their secrets, pushing the boundaries of human knowledge and redefining our place in the cosmos. The journey to understand black holes has only just begun, and the future promises to be as enigmatic and awe-inspiring as the objects themselves. Einstein's conditions of gravity provide the best depiction of a pivoting dim opening. He showed that a turning dull opening wouldn't implode into a point, as previously suspected, but rather into a ring of shoot or a slight circle. The plate would rotate so rapidly that outward forces would prevent it from collapsing. This alternating plate of matter is known as the ergosphere, the region surrounding the dim opening where the laws of physics begin to break down. However, the most fascinating feature of the Kerr solution was its prediction of the presence of an Einstein-Rosen bridge, otherwise known as a wormhole. This is a theoretical tunnel through space-time that connects two separate regions of the universe, or even two parallel universes. The idea is that if one were to fall into a dim opening, instead of being crushed to nothingness, they would be sucked down a passage through the ring of discharge and ejected out of a white opening into a parallel universe. To understand how this works, we need to examine the nature of space-time in Einstein's theory. The reality we experience isn't made up of separate entities, but is interconnected, forming a four-dimensional fabric known as space-time. Objects warp this fabric, creating a gravitational field that causes other objects to move toward them. Now, imagine a piece of paper representing space-time. If you put 2 points on the paper and draw a line between them, this represents how objects travel through space-time. But what if you could fold the paper and create a shortcut between the 2 points? This is the fundamental idea behind a wormhole, a shortcut through space-time that connects two distant points instantly. Wormholes aren't just a science fiction concept. They are a real prediction of general relativity, although no one has ever observed one directly. The reason is that wormholes are inherently unstable and would collapse quickly. However, the existence of an Einstein-Rosen bridge would mean that dim openings are not only massive vacuum cleaners, but could also be gateways to other regions of space-time. So, could we use a wormhole to travel through existence? Unfortunately, the answer is probably no, not yet. Even if we could stabilize a wormhole, it's unlikely we could use it to travel faster than light. Einstein's theory of special relativity predicts that the speed of light is a hard limit on how fast anything can move through space-time. Even so, the theory of wormholes and dim openings as pathways to different parts of the universe, or even to different times, has fascinated physicists for decades. The idea that there might be shortcuts through the fabric of space-time, allowing travel across vast distances or even into the past, could be revolutionary if we could achieve it. One of the most captivating ideas in this field of study is the CR wormhole, named after the mathematician Roy Kerr, who first described Einstein's equations of gravity. This type of wormhole is essentially a theoretical tunnel through space-time that could connect two distant points, such as two different universes or even two different times within the same universe. The Kerr wormhole is ring-shaped, like the mirror in Alice in Wonderland, and could theoretically transport a traveler to another universe or some other time where the laws of physics might differ from those we are familiar with. Yet, at the destination, these differences could be entirely normal. While the possibility of wormholes for interstellar travel or time travel is certainly exciting, it is also a topic of debate among physicists. Some argue that wormholes, especially Kerr wormholes, may be unstable or difficult to traverse due to the extreme radiation and subatomic forces surrounding their entrances. Critics contend that Einstein's equations of gravity, which describe wormholes and dim openings, only apply to gravity and not to the quantum forces that govern radiation and subatomic particles. To fully understand these phenomena, we need a new theory that can combine the laws of gravity with quantum theory. This is known as a theory of everything, a single framework that unifies Einstein's theory of gravity and quantum theory. Michio Kaku, a famous theoretical physicist, has been working on a theory of everything for years. While there are many versions of what this could be, one that has shown promise is string theory. String theory combines gravity with quantum theory, suggesting that subatomic particles are tiny vibrating strings, and that the universe is a collection of these strings. Just as different musical notes correspond to various vibrations of a violin string, different particles in nature correspond to different vibrations of a string. A fascinating aspect of string theory is that as a string moves through time, it warps the fabric of space around it, creating dim openings, wormholes, and other extraordinary solutions to Einstein's equations. This means that string theory not only unifies Einstein's theory of gravity with quantum theory, but also explains many of the strange phenomena we observe in the universe. However, there is a catch. The extra dimensions of spacetime required by string theory are so small that we cannot observe them directly. As we continue to study dim openings, another essential aspect to understand is Hawking radiation, proposed by physicist Stephen Hawking in 1974. This concept suggests that dim openings are not entirely dark, but emit faint radiation due to quantum effects near the event horizon. This radiation occurs because of interactions between virtual particle pairs that suddenly emerge from the vacuum of space. Normally, these pairs annihilate each other quickly, but near the event horizon, one particle can fall into the dim opening while the other escapes into space. The escaping particle appears as radiation, which theoretically could cause the dim opening to lose mass and eventually vanish, a process referred to as black hole evaporation. Although this idea is groundbreaking, detecting Hawking radiation remains challenging because it is so weak and difficult to observe. The study of dim openings also offers insights into some of the most fundamental questions in physics, particularly regarding the relationship between quantum mechanics and general relativity. While general relativity describes the large-scale structure of space-time, quantum mechanics governs the subatomic world. The two theories, however, are currently incompatible under the extreme conditions near dim openings, where both gravitational and quantum effects are significant. This discord between the two systems is one of the primary challenges physicists face in developing a theory of quantum gravity, which would unify these two perspectives into a single coherent model. Moreover, dim openings could hold the key to understanding the origins of the universe. Some theories suggest that the intense conditions near black hole singularities could provide a way to study the very birth of spacetime. If wormholes do exist, as suggested by some interpretations of quantum gravity, they could potentially offer a mechanism for traversing vast regions of spacetime. While such travel remains speculative, these ideas open new lines of inquiry that may one day lead to a deeper understanding of the universe's fundamental workings. The implications of wormholes and black holes extend beyond theoretical physics and into philosophical and even practical domains. If wormholes could be stabilized and navigated, they might provide humanity with the ability to traverse vast cosmic distances, potentially enabling intergalactic exploration. This could address the limitations imposed by the vastness of space and the constraints of light-speed travel. However, the stabilization of wormholes would require exotic matter with negative energy density, a substance that has yet to be discovered or created. This exotic matter would counteract the wormhole's natural tendency to collapse, keeping its throat open long enough for travel. While quantum field theory predicts the existence of such phenomena in small quantities, scaling it up for practical use is a monumental challenge. Beyond space travel, wormholes raise intriguing possibilities for time travel. According to certain interpretations of general relativity, a wormhole could theoretically connect not just 2 points in space, but also 2 points in time. This opens the door to fascinating, albeit speculative, questions about causality, paradoxes, and the nature of time itself. For example, the famous grandfather paradox asks what would happen if a traveler went back in time and altered an event in such a way that their own existence was no longer possible. Resolving such paradoxes might require entirely new frameworks for understanding time and causality, potentially involving theories like quantum mechanics, where probabilities and superpositions replace deterministic outcomes. Meanwhile, black holes themselves continue to captivate researchers as cosmic laboratories for understanding the universe's most extreme conditions. Observations of black holes, such as those made by the Event Horizon Telescope, have provided direct evidence of their existence and shed light on their properties. These studies not only confirm Einstein's predictions, but also push the boundaries of modern physics. One of the most exciting frontiers in black hole research is the study of quantum information and its implications for the so-called black hole information paradox. This paradox arises from the apparent conflict between quantum mechanics, which suggests that information about a system can never be destroyed, and the classical view of black holes as entities that obliterate everything that falls into them. Hawking radiation adds another layer to this debate. If black holes emit radiation and eventually evaporate, what happens to the information about the matter that fell into them? Does it disappear, violating quantum mechanics, or is it somehow encoded in the radiation? Recent advancements, including the concept of soft hair, subtle imprints of information on the event horizon, suggest that the information might be preserved, but a definitive answer remains elusive. Additionally, black holes and wormholes are being explored in the context of string theory and holographic principles, which propose that our universe might be a holographic projection of a lower dimensional reality. These theories could provide the framework needed to reconcile general relativity and quantum mechanics, offering profound insights into the nature of reality itself. As our understanding of black holes, wormholes, and the fabric of space-time evolves, the implications extend far beyond theoretical physics. They challenge our perception of the universe, time, and existence, inspiring us to push the boundaries of what is possible. The journey to unlock these cosmic mysteries may ultimately redefine humanity's place in the cosmos and offer pathways to technologies and concepts that seem unimaginable today.